So in the last session, we proved this theorem, which is called mean value theorem for harmonic functions. So again, there's a typo here. I did not correct it. I apologize for that. So it's not the border in the second equation, but it's the wall B. All right, and so today we are going to use this theorem in order to prove other uh, results. First, the strong maximum principle, the weak maximum principle, and the Harnack inequality. All right, so let's start with the strong maximum principle. So if we assume that u, so we assume that u is regular and the Laplacian of u is greater than 0, is non-negative, which is called a subharmonic function. And we assume that there is a point y on omega is a constant, such that u attains its supremum at y. Then you can deduce that u is a constant. Of course, if the same result holds if you replace subharmonic functions by superharmonic functions, but then you have to replace the second assumption with the supremum by the inf. All right. So let's prove now this result. All right, so we are now going to prove the strong maximum principle. So the assumptions are that Laplacian of u is non-negative. Of course, u is regular, and there exists y in omega such that u at y is the supremum of u over omega. Then the conclusion is that u is a constant. So let's prove this result. So to do that, let's consider first, let's call M the sup of u over omega and define the set omega m as the points in omega such that u of x equals m. Right, so our assumption is there is at least one element which we call y in omega. And we want to prove that, in fact, omega m equals m. And so omega m is not empty by assumption. Also, we can remark that omega m is a closet. Is a closed, sorry, is a closed, not a closet, is a closed is a closed set in omega, right? So if you choose a sequence of points in omega, which in omega m, which converge in omega m, then by continuity, uh, the limit is also in omega m. This is why this is because u is we assume that u is C2, so it's continuous. All right, so now let Z be any point in omega m. So we apply the mean value theorem to not u, but u minus m, right? We know that Laplacian of u is 0, is non-negative. So since m is a constant, Laplacian of m is 0. So also Laplacian of u minus m is non-negative. So we have that. Okay, so we can apply the mean value theorem, and we know that so 0 equals u of z minus m. This is because z belongs to omega m, and by applying the mean value theorem, we have that this is less than 1 divided this constant, the integral over a ball so it's in omega. Omega is an open, so I take a ball which is included in omega, and I obtain that. So this comes from the subharmonic functions, which says again this is like a kind of minimum, right? When the Laplacian of a function is non-negative, it says that the value at the center of a ball is less than the integral over the ball, right? This is the idea behind that. But then we note that since m is maximum, so m is the maximum value, so this quantity is non-positive. So I get that this is non-positive. All right, so what do I obtain? I obtain that the integral of u minus m equals 0. And since u minus m is non-positive, we have that u equals m all over the ball. So this implies that U equals M on B. All right, this means what? Therefore, for any Z on omega M, there exists an open ball such that Z belongs to B, belongs to omega M. So this means that omega M is an open set in omega. And it's not empty, but the only sets that are open and closed are are because by assumption, so omega is a domain, so it's connected. So and so the only sets that are empty and that are open and closed are the empty set and omega. But since omega M is not empty, it is omega. So therefore, omega is open, open, closed, and non-empty. Since omega is connected, so this is a topological result. We deduce that omega M equals omega. So this means that U is constant all over omega. So from the previous theorem, we can deduce the following results. So now, so if U is regular, if it's a subharmonic function, which means that Laplacian of U is non-negative, and we add that omega is bounded, then necessarily the supremum of U over omega is the supremum of U on the border. So why is that? So if the supremum of U is attained in the interior of omega, then U is constant. So it's true. And if it's not attained there, then necessarily it's attained in the border, and that's why this result holds. All right, so the last result that we are going to prove today is the Harnack inequality. So we assume that omega prime, it's a bounded domain strictly included in omega, and that U is a non-negative function, and it's harmonic. Then the supremum of U can be bounded by C times the infimum of U. So yeah, this gives you a control of the amplitude of U. All right, so let's prove the theorem, the Harnack inequality. So first of all, let y be a point in omega, and such that uh, the ball of radius 4r is included in omega for some positive number r. So you have omega, and you have here a ball center in y, and here you have 4r. And then let b x1 and x2 be any points in the wall of centered in y and of radius r. Then we apply the mean value equality. Since u is harmonic, Laplacian of u equals 0, and we have that u of x1 is 1 divided by omega n r to the n, and the integral all over the ball center in x1. So there I apply the mean value theorem. But since u is positive, and so not also that if let z, if z, just a remark, if z belongs to the ball of center x1 and radius r, then if I look at the distance with z, then thanks to the triangular inequality, this is less than dyx1 plus dx1z. And so this is r plus r to r, right? So which means that this ball is included in the ball of center y and radius 2r. So I can write that since u is non-negative, I keep my constant here, but instead of looking at the integral over br, I can put b2r and centered at y of u. Yes, right? This, all right. Okay, on the other hand, if I look, if I apply my mean equality at x2, and I look at ux2 is 1 divided by omega n, and I choose 3r to the n, integral b3r x2 u dx. So this is the mean equality. But then in this case, this ball here is included in this wall here. So let's write that this is greater than 1 divided by omega n 3r n and the same ball. So why is that? Let's just write it for a couple of seconds here. Because if z belongs to this ball, and if I look at the distance between z and x2, this is less than the distance between z and y plus the distance between y and x2, and this is 3r. Okay, so this now we have these two equalities, and what does it mean? Because x2 and x1 are any points. So for example, I can divide it here by 1 divided by 3 at the power n. So what does it mean? It means that if I divide here by 3 to the n, so here 3 to the n, here 3 to the n, then I have the same thing here. So this means what? This means that at any point u divided by 3 to the n is less than u. So I can say that for any u, it says that, sorry about that, this says that for any u is less than 3 to the n u of x2. So I can say that the can put here the inf and I can put here then the sup. Okay, but this is for in the wall centered in y and of radius r. So now to end the proof, we consider any open set which is strictly included in omega, and we choose any x1, not any, we choose x1 and x2 uh, in the closure of omega prime with such that u of x1 equals the sub of u and u of x2 equals the nth of u. And the idea now is to join. So let's say you have x1 here and x2 here. And so you join these 2 points by an arc gamma. And so we'll apply the previous result. So, but I want to ensure that I can choose a ball with radius 4r, which stays in gamma. So I choose r such that 4r is less than the distance between gamma and the order of omega. And so since omega prime is the closure of omega prime is compact, uh, I can always cover gamma by a finite number of balls. Of radius r. So I will cover my arc with a finite number n of balls. And then I apply um, inductively the previous results, and I'll get that u of x1 is less than 3 and n u of x2, right? Because I do ux1 less than ux1 prime, and so on and so forth, and at the end I get that. And so this is my constancy.